In the name of Allah, in this lecture, I will discuss the symmetrical components theory, and we will understand the difference between positive sequence, negative sequence, and zero sequence. Of course, this topic is one of the most important topics for a protection engineer. Of course, everyone knows that the electrical network begins with the power generation stations. Therefore, we understand that the generator is the main source supplying the electrical network with the required voltage and frequency. As a result, through the rotation and movement of the generator, it is able to provide the electrical network with a three-phase system, R, S, and T. Of course, the phase angle between each pair of phases is 120 degrees. To understand the concept of symmetrical components, we will focus on several very important points. The first point is the direction of rotation or the phase sequence of the three phases. The original direction or phase sequence for both voltage and current is counterclockwise. Therefore, the phase sequence will be A, then B, then C. This means that when moving counterclockwise, we will observe that when phase A starts rotating, the phase that takes its place is phase B, followed by phase C. In conclusion, the original sequence of rotation for the three phases is counterclockwise. In other words, phase A comes first, followed by phase B, and then phase C. Therefore, the phase sequence is ABC. The second important point is that there are 120 degrees between each pair of phases. It is essential to understand that, in practical terms, the angle represents time. Therefore, when the angle between phases A and B is 120 degrees, it means that the time duration for phase B to move into the position of phase A corresponds to 120 degrees. So, in a 50 Hz system, we know that 120 degrees corresponds to a time interval of 6.6 milliseconds. So, power generation plants are expected to produce electricity in a balanced system. This means that the voltage magnitudes of all phases are the same. The current magnitudes in each phase or line are also equal, and the phase angle between any two phases is 120 degrees. When these three conditions are met, we can say that the electrical system is balanced. Thus, electrical energy is transmitted to all parts of the power network in a balanced manner through a three-phase system, R, S, and T. However, it is essential to recognize the presence of another element throughout the entire power network, which is earth or ground. In other words, this refers to the grounding of the metallic bodies or enclosures of all electrical equipment and devices. However, with the use of power transformers and distribution transformers, as seen in the image before us, another conductor is present, which is the neutral line. Thus, we can say that the power network, in general, consists of 5 conductors. 3 conductors forming the three-phase system, R, S, and T. 1 conductor dedicated to the neutral line, 1 conductor dedicated to ground, earth, regardless of whether the neutral point is connected to the ground or not. I previously explained the difference between the neutral point and the ground point. The ground point is defined as a reference point with a voltage of 0 under all conditions. On the other hand, the neutral point is where the three phases meet in a star Y connection. Its voltage is 0, equal to the ground potential, if the electrical network is perfectly balanced in terms of voltages, currents, and impedances across all three phases. However, if the system loses its symmetry, such as in the case of a ground fault, the neutral point acquires a voltage relative to the ground. It is important to recognize that there is complete insulation between all these conductors, that is, between R, S, and T and the metallic body or enclosure of the electrical equipment, which represents the ground. However, under emergency conditions or faults, the electrical insulation may break down, leading to contact between any of these conductors. Such contact results in a fault or a short circuit. I previously told you about the types of faults based on the symmetry between the phases. They are symmetrical faults and unsymmetrical faults. As for symmetrical faults, they are defined as faults in which the current and voltage values in all three phases R, S, T are equal. They also refer to faults occurring between the three phases R, S, T, whether involving the ground or not. Thus, symmetrical faults consist of two types of faults. First, three-phase fault, which refers to faults or contacts between the three phases R, S, T. Second, three-phase to ground fault, three-phase to earth, which refers to faults or contacts between the three phases R, S, T with the presence of ground, earth. As for unsymmetrical faults, they are defined as faults in which the current and voltage values in the three phases R, S, T are not equal. They also refer to faults occurring between some phases and the ground or between phases without the presence of the ground. Thus, unsymmetrical faults consist of three types of faults. First, single phase to ground fault, which refers to a fault where a single phase contacts the ground. Second, double phase to ground fault, which refers to a fault where two phases contact the ground. Third, phase to phase fault, which refers to a fault where two phases contact each other without the presence of the ground. It is crucial for the protection engineer to study and analyze all types of faults, whether symmetrical faults or unsymmetrical faults. Although symmetrical faults are more severe than unsymmetrical faults due to the significant increase in fault current or short circuit current, they are easier to analyze in short circuit calculations. This is because in symmetrical faults, the current values in all three phases are equal, as well as the voltage magnitudes and phase angles. However, the biggest challenge for the protection engineer lies in calculating short circuit currents for unsymmetrical faults. As mentioned earlier, this is due to the differences in currents, voltages, and phase angles among the three phases. For example, if a fault occurs between a single phase and the ground, say phase R, will the other two phases, S and T, be affected by this fault or not? And what are the current values for both the faulty phase and the healthy phases? This highlights the importance of the symmetrical components method, as it is the only approach that allows us to analyze the behavior and distribution of fault currents across the three phases in the case of unsymmetrical faults. So, what is the symmetrical components method? I told you before that during asymmetrical faults, such as a single phase to ground fault, the electrical circuit loses its balance. This means that each phase carries a different current from the others, and the voltages also differ for each phase. To analyze this unbalanced system more effectively and perform short circuit current calculations, it is necessary to use the symmetrical components theory. The fundamental idea behind the symmetrical components method is that every unbalanced electrical network can actually be represented as three symmetrical networks: positive sequence, negative sequence, and zero sequence networks. By summing these three components, positive sequence, negative sequence, and zero sequence, the original unbalanced system is reconstructed. For example, we see an unbalanced electrical network or circuit in front of us. Naturally, we observe that the current or voltage values are different for each phase. Additionally, the angle between each pair of phases is not equal to 120 degrees. As I mentioned earlier, using the symmetrical components theory, we can analyze an unbalanced electrical circuit by breaking it down into three symmetrical circuits: the positive sequence, negative sequence, and zero-sequence networks. However, the important question is, why are these circuits called the positive sequence circuit, the negative sequence circuit, and the zero-sequence circuit? I previously explained that the natural direction, or the normal sequence, of the three phases is counterclockwise. From this, we understand that since the first circuit of the symmetrical components rotates in the same direction as the natural phase rotation, it is called the positive sequence circuit, meaning phase R followed by phase S, then phase T, as I explained at the beginning of the lecture. However, it is important to note that the phase angle between each pair of phases will be 120 degrees. However, the second circuit of the symmetrical components will rotate in the opposite direction to the natural phase rotation, meaning it will rotate in the clockwise direction. Therefore, because it rotates opposite to the natural rotation, it is called the negative sequence circuit. Also, it is important to note that the phase angle between each pair of phases will be 120 degrees. However, in the zero sequence circuit, we will observe that the phase angle between any two phases will be 0 degrees. So, what we understand is that when an asymmetrical fault happens at any point in the electrical network, the voltages of the phases R, S, and T will become unbalanced. This means that the voltage of phase R, VR, is not equal to the voltage of phase S, VS, and neither is it equal to the voltage of phase T, VT. Now, by using the symmetrical components theory, we can say that the voltage of phase R or VR is equal to the sum of VR positive, VR negative, and VR zero. Similarly, the voltage of phase S or VS is equal to the sum of VS positive, VS negative, and VS zero. And the voltage of phase T or VT is equal to the sum of VT positive, VT negative, and VT zero. Due to the presence of the fault impedance across the three phases, this means there is the positive sequence impedance, the negative sequence impedance, and the zero sequence impedance. Therefore, we understand that due to the presence of voltage and fault impedance, currents will flow in the three phases, and of course, these currents will be unbalanced. Following the same principle as voltage distribution in each phase, we will have 9 currents. This means there will be currents in each circuit representing a positive sequence current, a negative sequence current, and a zero sequence current. I emphasize that whether it is the positive sequence or negative sequence current or voltage, they will all be three-phase systems that are equal in magnitude, with an angle of 120 degrees between them, just like any normal three-phase system. However, the zero sequence current or zero sequence voltage will all be equal in magnitude but in the same direction, meaning the angle between them is 0 degrees. In the end, we can say that the symmetrical components method is simply a technique for analyzing and studying faults, not a method for designing protection devices. This means that protection devices will continue to measure the same normal voltages and currents on the three phases. However, based on fault analysis using the symmetrical components method, we will observe that the equations used inside protection devices for asymmetrical faults will differ from those used for symmetrical faults. Thank you for your attention. See you in the next lecture.